Fundamental research has been carried out by APV to study the effect of surface finish, temperatures, flow velocity and concentration on CIP cleaning times and costs for standard soils. APV have produced a short color video which illustrates some of the flow visualization work. In summary, the video shows by means of glass pipelines the effect of turbulence in two differing lengths of dead pocket, namely 76 and 127 millimeters. Three flow velocities are depicted, namely 0.3, 0.9 and 1.5 meters per second. In each case, the flow shown is directed into the pocket and then away from the pocket. Altogether, 23 sequences are considered as assorted configurations, and the video illustrates such features as air entrapment, air purge, valve cleaning, and soil removal. The video is annotated with appropriate symbols, and the expression L/D is used to denote the length of the dead pocket over the diameter of the pipeline. The video opens with a general view of small polystyrene beads circulating in a glass pipeline. The first sequence depicts a blank vertical T-piece with the flow directed into the pocket. The depth of the pocket is 127 millimeters. A flow rate of 0.3 meters per second does not give sufficient turbulence in the dead pocket for confident cleaning, but 0.9 meters per second and 1.5 meters per second provide an adequate cleaning velocity. Sequence 2 shows the flow at 0.3 meters per second moving away from the dead pocket, and the low turbulence is significant as poor cleaning will result. Adequate turbulence is obtained at 0.9 meters per second, and there would be no problems in cleaning. The same is true for 1.5 meters per second. Sequence 3 shows the depth of pocket reduced to 76 millimeters, and here cleaning is satisfactory at all velocities. Sequence 4 is again a 76 millimeter depth of pocket with a flow away from the pocket. Cleaning is adequate at all velocities, but the lower turbulence should be noted particularly at 0.3 meters per second. These four sequences emphasize the importance of directing the flow into the dead pocket. Sequence 5 shows an inverted blanked T-piece. This is a very bad condition, and particulate matter or scale particles fall into the dead pocket. When the flow velocity increases to 0.9 meters per second, turbulence increases and much debris is lifted and removed. However, 1.5 meters per second is obviously superior as turbulence is increased. The suitability of this type of orientation is always in question. In sequence 6, the depth of pocket has been reduced to 76 millimeters, and the rotating cartwheel effect is noticeable. With increased flow velocity at 0.9 meters per second, the scouring action in the corner of the pocket is improved and cleaning is fairly adequate. The same is true for 1.5 meters per second. In sequence 7, flow velocity of 0.3 meters per second into a horizontal blanked T-piece of depth 127 millimeters is seen. Here, the turbulence is not good in the blanked pocket. However, at 0.9 meters per second, the flow into the pocket is improved and the cleaning is satisfactory. In sequence 8, the flow is directed away from the pocket, which is of depth 127 millimeters. The turbulence is reasonably good, but at 0.9 meters per second the turbulence has not increased greatly in the dead-end pocket. Similarly, at 1.5 meters per second, the flow in the main tube is satisfactory, but the turbulence in the dead-end pocket is not good. In sequence 9, air bubbles are becoming trapped at the top of the pipeline, even though the flow is into the pocket. This occurs at the flow velocity of 0.3 meters per second, and even when the depth of pocket has been reduced to 76 millimeters. It can be seen that at 0.9 meters per second, the air bubbles are removed and very good cleaning is achieved. Sequence 10 depicts cleaning across the head seal of an automatic valve when the flow velocity is 0.3 meters per second. This work was carried out as part of an investigation into the cleanability of valve head seals. When the flow is reversed in sequence 11, the flow at 0.3 meters per second can be seen across the shaft of the valve. Obviously, the convolutions are not present in the typical industrial automatic valve. This work was associated with the cleanability of valve stems and associated shaft seals. Sequence 12 represents a vertical blanked pocket of 127 millimeters depth, and immediately one can see that trapped air bubbles have created a very difficult cleaning problem. At 0.9 meters per second, there is still inadequate cleaning, and even at 1.5 meters per second it can be shown that flow, and thus chemical solutions, do not reach the top of the blanked pocket. Under these conditions, effective CIP is impossible. This is an important feature, as many companies often advocate assembling pipelines as one huge serpentine loop, and the cleaning of all valve manifolds in one stage without any valve pulsing. In this videoed sequence, instead of a blanked dead end, the top of the dead pocket could be a valve seat on a valve manifold. If the valves are not pulsed during CIP, and adequate product protection maintained during this process, air will remain trapped during the whole of the CIP sequence. Thus, successful CIP is not merely a question of cleaning across the seats of the valves, but is frequently associated with the removal of trapped air pockets. In sequence 13, the flow is now directed into the pocket of depth 127 millimeters, but at 0.3 meters per second, the top of the pipeline is not being cleaned. At 0.9 meters per second, the velocity is inadequate for good cleaning, At 1.5 meters per second, the cleaning is just about adequate, can be considered as roughly equatable to conditions in a vessel when the spray ball discharges. This would produce satisfactory cleaning given adequate contact time. In sequence 14, even though the depth of the pocket has been reduced to 76 millimeters, at 0.3 meters per second the top of the pipe is again not cleaned. However, with the flow into the pocket and the length relatively short, adequate cleaning is obtained at 0.9 meters per second. But it can be seen that when the flow is increased to 1.5 meters per second, all air bubbles are removed and the flow is obviously more suitable. Sequence 15 shows the flow away from the pocket, and 0.3 meters per second is quite inadequate. 0.9 meters per second is fairly acceptable, and 1.5 meters per second shows good removal of air and gives adequate cleaning. In sequence 16, the difficult situation is obvious. This is a vertical T-piece blanked off at the top. One air bubble comes in and one air bubble goes out. The vertical pipe remains soiled, and even at 0.9 meters per second and 1.5 meters per second, the cleaning is totally inadequate. In sequence 17, the depth of pocket has been reduced to 76 millimeters, and although 0.3 meters per second and 0.9 meters per second are inadequate, it can be judged that 1.5 meters per second is possibly acceptable when viewed as being similar to the spray ball discharge in a vessel. These sequences show air purge and a slow-motion video of a discharge at 1.4 bar. 1.4 bar is considered to be inadequate for normal air purging, as may be seen in the actual speed shown in the next sequence. Too much product is left in the pipeline. However, at the more normal pressure of 2.8 bar, the slow-motion discharge is evident and the pipeline is relatively clear of product. The actual speed is then shown. Systems must be designed for air purging, and it's unsatisfactory to blast air in a pipeline and claim that air purging has been introduced. In sequence 19, the camera shows removal experiments, including the removal of a plug of butter in a pocket 76 millimeters deep, using water at only 60 degrees Celsius. The digital clock appears in the right-hand corner of the screen. When the flow is established, the bottom right-hand corner of the butter plug is lifted by a combination of flow velocity and melting of the butter, while the plug is removed en masse within a relatively short period of time. Complete soil removal is obtained in approximately 6 seconds. In sequence 20, the depth of pocket has been extended by an additional 50 millimeters to 127 millimeters. Although flow is into the pocket, product removal will obviously take time. Within certain CIP systems, this rinse water will be continually discharging to drain, whereas in recovery systems, the rinse is capable of recirculation, thus isolating a high BOD loading or enabling product recovery to be considered. Soil removal is not necessarily a wearing down of the soil load, but removal of debris as the turbulent action continues. In this instance, 1 minute 58 seconds elapse before the plug of butter is removed, should be compared with the 6 seconds in the earlier sequence. In sequence 21, the main flow is directed away from the pocket, which is maintained at 127 millimeters. This will produce a much longer time for soil removal, and the digital clock shows that it will take 2 minutes 51 seconds before all soil is removed from the dead-end pocket. Sequence 22 shows milk in a dead-end pocket of 127 millimeters depth with water flowing into the dead-end pocket. Here, the total pre-rinse milk removal is achieved within 6 seconds. In the final sequence, milk is placed in the dead-end pocket of 127 millimeters depth, and the flow is discharging away from the pocket. This should take longer, and indeed the total time for removal of milk in this pocket is approximately 15 seconds, or twice as long as in the earlier sequence.